Hi, I'm Lucia, and today I'm going to be presenting our work on constrained spectral uplifting for HDR environment maps. So to start off, I'll give a bit of background on spectral rendering, move on to spectral uplifting, and the motivation behind our work. So when you're using an RGB render, its material properties are represented as a tristimulus value. And however, this is not what happens in nature, where material properties such as reflectance, transmission, etc., are represented as a distribution of wavelength. And this is what spectral renderer does. So it simulates this type of behavior, and therefore it results in more accurate light transmission, so more physically accurate results. Another motivation to use a spectral renderer is in the VFX industry, where it is common to switch between plate footage and its RGB counterpart. And if the RGB counterpart is only and its digital counterpart, and if it's only an RGB counterpart, it's not capable of preserving all the artifacts caused by real life light transport. And so you can see this on the image. If these two were constantly switched in a movie, this would be really undesirable. So it's quite obvious that we want to use a spectral renderer. When you're using a spectral renderer, you need to use spectral assets such as textures, materials, and environment maps. And obtaining them is not an easy task. And even if it were, the 3D artists are always going to be painting assets in RGB, modeling in RGB, and also a lot of RGB assets, environment map already exist. So the common workflow is to create these assets in RGB and then to convert them into the spectral domain. And this process is called spectral uplifting. However, multiple different spectra can evaluate to the same RGB value, which makes spectral uplifting an under-constrained problem, and this may result in metamerism, as you can see on the images. So all of these were actually obtained from so you had an RGB image, and all of the assets or textures were uplifted with distinct uplifting techniques, and you can see that these are all quite distinct. So one of the main motivations of a spectral uplifting technique is for the results to be basically identical or very similar to what would happen in real life. And so one of the, for uplifting of general reflectances, so the input RGB values are between 0 and 1, bounded by 0 and 1. Probably the state-of-the-art technique can be considered the one by Jakob and Hanika, presented in 2019. They proposed an uplift model that is created prior to rendering, and it is an sRGB cube that is divided into evenly spaced voxels. And every one of these lattice points contains a mapping from its coordinate or its RGB value to a set of free floating point coefficients that are then able to reconstruct a reflectance curve with the help of a low-dimensional parametric model. And to uplift an arbitrary RGB value, basically the voxel the RGB value falls into is found, and the spectra at the corners are interpolated. So this all results in, I don't know why it's doing that, sorry. And this all results in smooth and simple spectra that are usually found in nature. However, while there has been a lot of research going on for reflectance uplifting, there hasn't been really much going on for emission uplifting. And this is mainly because the main light sources of a scene are generally uplifted manually, so by measuring their spectra with a spectrometer. However, this is impossible to do for the case of image-based lighting or HDR environment maps. So currently the state of the art is basically you get an HDR value, you scale it into the low dynamic range, you uplift it with an existing reflectance technique. So for example, the one I've talked about previously, and then you scale it back into the high dynamic range. And while this is technically correct, the results are nowhere near what would actually happen or what would the measurements be like in nature. Once again, this is a demonstration. These colors aren't that different if you look at the slides, but if the whole environment map were to be uplifted in this manner, it would be even more evident. And even these are slight differences that would be noticeable in the if you were to switch that in a movie. So moving on to the motivation. So our goal is to uplift these environment maps so their emission spectra would be similar to that, to their measurements. And we base our work on a very simple observation about environment map captures, and that is that the emission of individual pixels in the capsule in the capture is due to an emission of a light source rather than the emission of the objects themselves. And what this means is basically that if you look at the environment map, the only source of light there is the sun. However, all of the pixels that are visualized in red are HDR, so they have emissive properties. And this is not because the table or the ground is emissive in itself, but it's rather because the light from the sun reflects of these objects, making them emissive in the capture. So this results in a simple equation that the final pixel uplift is a multiplication of the reflectance of the object the pixel belongs to times the incoming emission from all the light sources in the scene. So our technique has two steps. One is to detect the emission, and another is to detect the reflectance. So the first step is light source detection. So we detect the light sources in the scene and in the end map, and we obtain their emission spectra. And we do this with the following process. So you get an input environment map. Now I'm giving an overview, then I'll dive into individual steps a bit more. So you get an input HDR map, you do sky segmentation, then you do what we call light source clustering. So you find the main light sources of the env map, and you find the pixels that are most influenced by these light sources. Then for each of these clusters, you determine whether they have indoor or outdoor illumination. Then you move on to finding their correlated color temperature. And from all of this information that we obtained about individual clusters, we find the most viable emission spectrum for the light source from a database of spectra. Moving on to the individual steps. So the sky segmentation is performed by a technique proposed by Shen and Wang in 2013, which was sufficient for our purposes. Probably the most noteworthy part of the pipeline is the light source clustering, and we did this actually by looking at the visualization of the HDR pixels in the 3D RGB space. And I'm showing some of them on the slides, and if you look closely, you can see quite evident clusters forming in the high dynamic range. And this actually makes sense because the light sources are of slightly distinct temperatures. And they throw distinct color casts on the pixels or on the objects that they influence most. And while there isn't much difference in the low dynamic range, this is quite noticeable, or in the high dynamic range, the RGB differences here are quite distinct. So we found these clusters by performing a modified version of the k-means clustering algorithm, where we force the clusters to form around certain axes as opposed to around certain points. And we use some additional heuristics to determine the most optimal number of clusters. Afterwards, we assign the indoor-outdoor flag. That's the result of the sky segmentation. If the cluster contains a portion of the sky, it is going to be an outdoors, otherwise it's an indoors cluster. Then we moved on to the CCT detection. That's the correlated color temperature of the light source in the cluster, and we determined that to be the cluster mean with some additional heuristics. And lastly, we move on to finding the actual emission spectrum for the light source in the cluster, and we do this according to this diagram. So outdoor clusters are divided into sunset and daylight clusters, depending on the CCT, warmer for sunset, cooler for daylight. And unfortunately, for the indoor clusters, we couldn't, based on this two information alone, we couldn't determine the actual type of the illuminant. So we just support, by default, we just assume everything to be LED. However, we also support fluorescent and incandescent light sources if specified by the user. And for every one of these categories, the final emission is obtained slightly differently. For the sunset category, we obtain sunset spectra from the Prague sky model, and we perform interpolation depending on the CCT. For daylight, we use the daylight D-series illuminant calculation. For both fluorescent and LED, we comprised a database of spectra, from actual real-life measurements, and we use their interpolation. And finally, for incandescence, we use the Planck's law. So that is how we detect the light sources. And once we have that, we can move on to the actual per pixel uplifting. So once again, to recap, the final pixel uplift is a multiplication of the reflectance of the object the pixel belongs to times the incoming emission. We make a simplification that this incoming emission is only a result of one light source, and that is the cluster's light source. Therefore, what remains to be determined is only the reflectance. And we find this we use an existing reflectance uplifting technique to determine this. We use actually the one by Jakob and Hanika, proposed that I've already talked about before. That was the cube uplifting technique. The only problem with this technique is that it was designed for the D65 illuminant, which means that all of the spectra that are stored, so we have those RGB to spectral mappings, the spectra evaluate to these RGB values under the D65 illuminant. But we already found a distinct illuminant in the scene, and we want to use this one. So that's the one we found with the light source detection. So what we do is that for every cluster, we convert this D65 model to a model of this new illuminant. And we do this by simply reconstructing all the mappings and storing them, reconstructing all the mappings and storing their RGB values under the new illuminant. So we have new mappings and a new 3D model. And this obviously skews and scales the model. So this results in some technical difficulties, but the average case complexity remains the same and everything. So the uplifting in the new model is performed in a similar manner. So just to summarize, once again, we get an input environment map. We perform its light source clustering. For every cluster, we find the emission spectrum of the light source, as you can see on the left. Then we create this reflectance uplift model for every one of these emission spectra. And after all of this is done as kind of a pre-process. We can move on to per pixel uplifting. And for every pixel, we find the cluster the pixel belongs to. We find the reflectance uplift model for this cluster. We use this to uplift the reflectance of the pixel. And to get the final uplift, we multiply it with the emission spectrum, as you can see on the right. Now, moving on to the results. So when testing the correctness of an uplifting technique, the most important benchmark is the uplift accuracy or the round trip accuracy. And that is basically the difference between the RGB value we are uplifting and the RGB value the uplifted spectrum evaluates to. We tested this by uplifting over 150 environment maps on distinct settings with distinct light sources and so on. And we used the delta E 2000 error as an error measure. And delta E under 1 is generally considered negligible, and you can see that therefore our results are extremely negligible. And this basically means that this technique is technically sound and can be used for the purposes of HDR and map uplifting. However, probably the more important part is how it compares to the current state of the art, so the scaled reflectance uplifting. And to test this, we compared the following 3 spectral environment maps. First, we rendered an environment map and stored its spectral variant. This we call the ground truth. And then we used the RGB variant of this ground truth and applied both our uplift and the scaled reflectance uplift. And we use all of these 3 environment maps when rendering a scene. So for example, you can see this on the scene here. The top line is the scaled reflectance uplift versus the ground truth, while the bottom line is our technique versus the ground truth. The delta E images or the difference images on the right are relative to delta E5, which is already quite noticeable. And if you look at the cars, you can actually see it. So this shows that obviously our technique outperforms the scaled reflectance uplifting quite a bit. Unfortunately, we do not have many tests of this sort, and this is simply because obtaining environment maps in this manner is extremely tedious, so obtaining these spectral environment maps with the renders. And also, we did not have access to hyperspectral cameras, so spectral captures of environment maps. However, here I'm showing, on this next slide, I'm showing a comparison of actual uplifts of some of these pixels of the end map to where we compare, once again, the ground truth to our uplift and scaled reflectance. And you can see that our uplift is extremely similar to the ground truth, while the scaled reflectance is, it's quite a significant difference. And so while we cannot provide a conclusive measure on of the similarity of the ground truth to our uplifting, we can provide a measure of the difference between the scaled reflectance uplifting and our uplifting. And we did this by, once again, uplifting over 150 environment maps, which means that we got over 4 million uplifted spectra. We also obtained over 3,500 reflectances from existing reflectance measurements, so from the classic color atlases such as Mansell Book of Colors, Macbeth color charts, and so on. And what we did is we actually compared the RGB value of these reflectances under our uplifts versus the scaled reflectance uplifts. And the average error here was delta E 1.5, which is already slightly noticeable. However, the even more meaningful thing is that the maximum delta E was sometimes even over 20, which is basically a different color, and sometimes even 40 for some specific saturated colors from the Pantone Color Atlas. So while we cannot claim that this is exactly the type of error that our method fixes, because we did not have, what would be ideal would be to have these ground truth renders here as well. The nature of our technique suggests that the actual values are going to be pretty similar to this. And that's basically it. So in conclusion, we presented the first method capable of uplifting HDR maps according to real-life data. There are some slight limitations to our technique that are basically some of the steps of the pipeline lack precision in some specific corner cases. This is mainly in the clustering and CCT detection. However, we do not consider this a major problem simply because the main aim of this paper was rather on the uplifting than on of these specific steps of the pipeline, so clustering or CCT detection. So this is something that can be focused on in future work. And another limitation that we are going to be working on as future work is the lack of validation data, and basically the ground truth, as I've already said, and also the performance that, as we did not have access to an actual spectral renderer, we cannot really claim how much this will decrease the performance.